So let me introduce our speaker this morning. Guzin Bayraksan is a professor in the Department of Integrated System and Integrated System Engineering. Her papers have appeared in top journals such as Mathematical Programming, Operations Research, Journal of Optimization. She's supported by the National Science Foundation and the Department of Energy. She won several awards in the last 10 years. In particular, in 2012, she obtained the NSF Career Award, followed by the Inform's ENRE Best Publication Award in Environment and Sustainability in 2016, and the Loonley Research Award. So congratulations, Guzin, for all these achievements. And since 2009, Guzin is also chair of the Stochastic Programming Society. So she's been involved in the field of stochastic programming and distributionally robust optimization for approximately as long as me. It's a real pleasure to have you with us today, Guzin. Thanks for accepting the invitation and making some time in your schedule to be giving the talk and participate in the workshop. The floor is yours.
Thanks, Eric, for this nice introduction. And I really want to thank the organizers, Eric, Walter, and Fabian, for this really fantastic workshop. It's been wonderful so far. Hopefully it continues as well. Today I will be talking about, it's 45 minutes, right? Before that's what we're aiming for.
Sure. Yeah.
All right. Please warn me. I've got a lot of slides. So I will be talking about data-driven sample average approximation with covariate information. So these are the side information that we can utilize to make better decisions. And this is joint work with Rohit Kannan, who is now a postdoc at Los Alamos National Lab, and Jim Lutke, who's a professor at University of Wisconsin-Madison. Yes, gratefully acknowledge the Department of Energy grant here. I actually did a little bit, put an ambiguity set around my abstract that I submitted. So I also included some things that are related to it around the same area. My talk was about this, but I'm hoping to cover also, as time remains, distributionally robust version of this as well. All right, so let me start by introducing the notation that we're going to be using, which is slightly different than a traditional stochastic program notation. So here, we're going to reserve the capital Y, capital X, more in the statistical terms, like they're random variables, random vectors. So in the traditional setting, we're making some decisions. For example, it's an inventory production decisions subject to this set of constraints, minimizing our expected cost, where, for example, we do not know the demand of our products. So these are the random parameters denoted as Y. Of course, this is a very difficult problem to solve, even calculating this expectation. So in a data-driven setting, and suppose we have access to some perhaps historical demand observations, N of them, they can be independent, identically distributed or not. And what we do is we replace this expectation, which is very, very difficult to calculate even for a fixed decision, Z, let alone optimize, right? So we replace it by the sample average approximation and solve this. And this is a very well-established framework with lots of theory, especially the book by Shapiro, Dancheva, and Brzezinski has really a very good result. I mean, like everything, and then all the proofs. And so if you really want to learn, like this is an excellent, excellent reference, and this is more like a literature survey. All right, so that's not the problem we're going to be looking at. What we are going to be looking at is stochastic programs with covariate information. So this is a conditional stochastic program. So in this case, so for example, in the inventory problem, we don't know the demand of our product. Suppose it's a brand new product, especially, but perhaps we have some historical data based on launches of similar products. Perhaps we introduced a product at a convention, and send it to social influencers or something. And then they started tweeting, people started retweeting. So we collect this web chatter data. And then we have a lot more information. Now we can use those side information to estimate our demand. So given that new information that we obtained, or even like past information, etc. So we plug that in. Now we want to solve, we want to make our inventory decisions by minimizing our expected cost, right? So these are in different communities, they're called like in machine learning, typically features. I've been also using side information, auxiliary information, or covariates. Our notation, you know, as I said, X and Y are more in the statistical sense, and the decisions now became instead of little xz. This notation is borrowed from this nice paper by Bayraksan and Kelly. All right, other example applications, and there are many, many of them. So Eric actually has a number of papers on this robust or not. So portfolio optimization with side information, right? This is, we don't know the return of the stocks, but we can use economic indicators, some publicly available company data, other things that are, you know, a lot of analysts are using. And then we use these information to estimate the return of the stocks. But in the end, we want to make our portfolio decisions to maximize our profits. Similarly, for the power grid scheduling. So for example, when we have renewable energy, we don't know how much wind power or solar power will be generated because they're variable. So we use weather forecasts and other things to, as covariates, to estimate this, but ultimately make generator decisions. All right. So we want to form an SAA with this, right? Just like before we used only data on, say, those demands or YI. Now we have the demands and the covariate information. So one observation is formed by both of these. So, and they don't have to be IID data. So given this, how do we form the SAA? Especially, we observe a new covariate. So this is historical data. We have a new covariate. It might be something we observed or something we have never seen before, and typically something maybe we haven't seen. And then we want to form a sample average approximation given this data. There are two components, right? So first, we need to learn. We need to predict Y given X, and then we need to integrate it into the optimization. So this is a topic that has been gaining more and more, in recent years, it's been increasing, getting increasing attention. So one option is to do something called like basically like what a machine learner would do, try to learn the solution. So give me the covariates, I want to map it to some optimal decisions, right? Here it has been used for news vendor problem, but in this paper, the authors basically show that this method can be problematic in certain ways, can cause infeasibilities, non-convexities, etc. So might not work very well. A second approach, which is really, I think, one of the easiest, and it seems to work pretty well. So it modifies the optimization step. So leave the machine learning, whatever statistical learning part as it is, but take some information from there and modify how you do the optimization with respect to this, because you have that conditional program. For example, Surajit has this learning enabled optimization and many papers there as well. I only put one. Another paper by Bun and Bayraksan and Kelly also work in this case. Our work also belongs to this category. You can go a step further, or another approach, I should say, right? You can modify the learning step. So this one wants to learn only the things that are important for the optimization model. Usually a much more challenging problem, can also be less modular, but the hope is like it will give better optimization decisions. All right, so this is very modular, easy, a lot, actually used a lot in practice. And there are, even within this, there are different ways to do it. And I'm gonna now explain what are we doing. All right. So first of all, we make this relationship assumption between our unknown parameters, let's say the demands and the covariates. x, right? So given a particular covariate realization, little x, we assume it can be defined by this, where this is the unknown, but true regression function. So if I know the covariate, I can get the conditional expectation of y given x. And there's an additive error term. And this additive error term, of course, by usual assumptions, have error expectation is 0. So for the regression function, we do not make too many assumptions, although later I'm going to give you some properties it has to satisfy, but it can be anything. However, in this talk, we make a majority of this talk, right? We make the assumption that the errors are independent of the covariates. All right, but this can be relaxed. Okay, so given this structure, we assume this. Now, this is our conditional stochastic program that we want to solve. But if I know this true relationship, I can actually replace it with this. So if you look at, if I know the true regression function and I know the distribution of the errors, it's just basically turns into a regular stochastic program, right? And again, to do a sample average approximation of this, maybe if I have this data, not necessarily ID, right? And I know obviously, if I know the true regression function, then given this training data, I can calculate the true, some observations of the true residuals, and I can form a sample average approximation of this problem, right? And how to do that, I basically use this assumed known regression function, and I plug in some data, the observations, the n observations of the residuals, and minimize the sample average approximation. So, of course, the problem is I don't know this regression function. So what are we going to do? We're going to estimate it by our favorite method. So this method, the residuals, empirical residuals method that I'm going to talk about has been proposed in the literature by Surajit and also in the one of the papers of Ban. So the first step is, of course, we don't know this, so we use our favorite method to estimate it using n data. And here's one example where we minimize some loss function. So let's say this is a squared loss function, so this can be least squares, but it can be anything. So we do not, use your favorite method. Once you do this, then given this training data, yi, xi at every point here, we plug in our estimate, and then we calculate these, what we call empirical residuals, right? So of course, there's some bias in this estimation and so on and so forth, but at least we can calculate them because we do not have access to the true residuals. Now we observe a new covariate and we want to solve the conditional stochastic program. So what we do is we take our regression estimate, evaluate it at the new covariate, and add these residuals. So this now, this n data point, forms a proxy, an approximation for samples of y conditioned on x is equal to little x. Okay, so even though there's some bias, etc., this is something we can do, and we can do it very easily. All right? So what I'm going to talk about next is some general analysis of this sample average approximation problem, which I call empirical residuals SAA, or short is ER-SAA. Okay? And then, as I said, as time remains, I'm going to hopefully talk about some improvements when the sample size is small. Okay. So to do this, let me show you the problems of interest, right? Especially, this is a problem we want to solve, right? But we don't know the regression function, but if we knew everything, and if we could actually take this expectation, minimize it, so wishful thinking, we would get this optimal value. Instead, what we can do is this problem, right? The empirical residuals based SAA. And if we solve it using n data points, then we get an optimal value that is, of course, statistical in nature. It depends on the sample here. Now I can ask the questions, okay, what are the conditions that this quantity will converge to this quantity in some probabilistic sense, and questions of this kind. Of course, in the middle is this full information SAA where if I knew the regression function, and I could use the actual residuals in this problem. So, and a little bit more notation here. So this is the set of optimal solutions to the true problem. This is an optimal solution to the ER SAA, and this is the set of optimal solutions, right? So we ask the same questions again. So the set of optimal solutions here converge in some sense, right, to the set of optimal solutions here, and so on and so forth. So to do this, I'm going to show you next a sequence. So this is the sequence of problems, but I'm going to show you a sequence of assumptions that allows us to do this. First of all, we need some assumptions on the type of problem that we solve. Second, if we know, like, we need some kind of nice properties of our estimator, if we knew everything. So for example, the data collection, something needs to be done in such a way that even if I know everything, I have good behavior, like this converges. Right? If I don't have that, then I don't have anything. The third thing, obviously, is that my estimation is good in some sense. So the first one is we have this assumption on the costs. So we need some Lipschitz continuity assumption on the costs here with respect to the unknown, let's say, demands or unknown parameters with the Lipschitz constant that satisfies this property. So this is satisfied under very mild conditions for, let's say, two-stage stochastic linear programs, or it could have integer variables in the first stage. We can relax this assumption to local Lipschitz continuity rather than global as in here. But in this case, we need a little bit more stringent conditions on the regression step. So these are needed to bound the error of our estimators with this empirical residuals. All right? And then, of course, we also need some conditions like the sampling. It doesn't have to be IID, but for example, alpha mixing, some other things that, and maybe some conditions on, again, on the structure of the problem, so that if we know everything, we can converge uniformly, the optimal values here converge uniformly on the set of feasible decisions, right? So there are many conditions and many different varieties of these conditions stipulated already in the traditional SAA. So we need some of those, okay? And of course, thirdly, we need our estimator, the regression estimation, to be good. For example, we need to have pointwise error consistency. So here our results are given in convergence and distribution. So our regression estimator for almost every covariate realization, for example, converges to the true one or in the mean squared estimation error as well. And these have been studied extensively in statistics, etc. literature, right, under appropriate conditions. So if we have these things, right, under some smoothness assumption or sufficiently, good problems with good estimation, then we can basically recover the traditional sample average approximation results where the optimal value of the ER-SAA converges to the true optimal value in probability. Some similar thing can be said on the set of solutions, right? So we get this asymptotic optimality consistency type of results. We can also strengthen them, for example, for rate of convergence. Before we needed our regression function to converge or its errors to go to zero in a probabilistic sense. Now we need the rates of them. Again, these have been established in the literature for some of these methods, right? Not all of them, but for some of them. We assume this big O of P in probability, there's some rate n to the power alpha that this convergence occurs. One thing to note here is, for example, if I have a linear function here and I use like a linear ordinary least squares, like a estimator or a lasso, then this is satisfied with alpha equals 1. However, if we use a more general that can, like k nearest neighbor or random forest, we can go beyond the linear thing. We can handle nonlinear functions here, regression functions, but we pay a price, right? So this O1, we denote by some generic constants, we denote them by O1. But there's 1 over dx. So as the dimension of the covariates increases, we pay a penalty here in terms of rate of convergence, the curse of dimensionality. Okay, so under these, once we strengthen the assumptions on the regression part, plus we need some central limit theorem on the SAA objective functions, right? Then for a given Z decision, right? Then combining those two, we can get some kind of a rate of convergence on the optimal value of the empirical residuals, right? So the convergence here, so now we had big O, now it's little o, so it will go to this one, converge to the true optimal value with this rate, right? So this is hiding some terms here, but that alpha shows up in this fashion, okay? As I said, this is hiding some things. We can take a closer look at this and we can do a finite sample analysis. And here, this is going to basically look at this, right? So I solve my empirical residual SAA and I look at the set of optimal solutions at the given new covariate X. Now I ask, is this a subset of, this is not the optimal set, this is a kappa optimal set. So it's a little bit enlarged, right? So is this a subset of the kappa optimal solutions to the true problem? Okay, now I want this probability, right? These are all kappa optimal solutions. I want this probability to be, let's say, at least 95%. What is the sample size required for this? Clearly, this is a theoretical concern, not practical, because it's very conservative, because this has to be satisfied, with a very large probability. But again, there has been a lot of work, Shapiro, Tito Hernando Mello, Anton Kleivecht. So these give insights into what's happening, although they may not be used in practice, right? So good insight. So we have here two effects. We use the union bound. So basically, part of the sample size we have from the traditional or classical SAA. So classical, so I denote it by NC. Some terms are hidden here. I'm not giving all the details about the variances and stuff, but obviously there's a dependence on this kappa optimal and the reliability level and so on and so forth. But we have a second component. The second component is because we also have a learning part. So we need some data like sample size, right? Additional samples to do the learning correctly as well. So let's take a look. If, for example, our regression function is truly linear and we use the correct model, so we use ordinary least squares and fit a linear model to this, then the dependency on the dimension of the covariates is also linear, more or less, right? Here. By the way, this is the classical plus. These are the additional samples we need for the learning part. However, if we have linear, but it's sparse, we don't need all the covariates, it's only a small number of them, then in this case, we are doing much better. We are actually depending on the covariates, dimension of the covariates in a logarithmic fashion, but we also have to multiply by that. And this is where the dy comes in. So if we go beyond the linear case, right now we can go nonlinear, but Lipschitz continuous and use k nearest neighbor. So this is significantly more general, but the k, the number of neighbors we use has to increase in this fashion. Then you can see it gets a lot more complicated. So we've got terms, dimension of y to the power dimension of x and etc. So, as the problem size gets bigger, you can get into more trouble. So that's the moral of the story, right? Because we have a learning, we need additional samples. And if we have a good, for example, a linear and we fit linear, we know the functional form and do this correctly, then the dependence is more modest. If we use more general models, regression, but we have to pay a price for this, more dependence on the dimensions of X. All right, let me see. So, okay, I do have time. So computational, let me show you some computational. On this. So we implemented this on a two-stage resource allocation model, or a variant of this from a really nice paper of Jim's. So our the demand vector is the Y vector is 30 customers, demands of 30 customers, and they depend on each other through these covariates. So here's what we did. So it's a demand of customer J is we generated the demands ourselves, and there's some normal errors here, additive normal error, and we have actually used 3 covariates. So there are 3 covariates underlying every one of these 30 different customer demands, and we use this parameter theta. So if the parameter theta is equal to 1, so the demands depend on this in a linear fashion. Okay. But we also looked at nonlinear model where this is like square, right? So it's depends on it quadratically or the square root. But no matter what theta is, we always fit a linear model. So sometimes our model is a correct model that is fitted, and sometimes it is not. Okay. One other thing I need to mention here, the dependence is only on 3 covariates, but we threw into the learning part the 3 that is needed, or 10, or we actually threw in 100, but only 3 are the ones that have an effect on the demands. Okay, so we solved our empirical residuals SAA and looked at its solutions, optimal solutions, and we estimated an optimality gap. Okay, so let's take a look at what's happening here. So here's what we do, ER SAA problem with ordinary least squares. As I said, we always fit this, but here we fit it to the model that's also linear. So it's the correct model fitted to the the linear. So these are the red ones that you're going to see here. The black one is the reweighted sample average approximation, but it uses KNN of Bayraksan and Callis. So what is this doing? Let me see if I can, let's see. So for example, this will like minimize. So what it does is it creates a sample average approximation, but instead of giving 1/n weight, it gives, for example, given the covariate, some weight I, something like this, and then there's a cost function, right? So just something like that. So a regular SAA, basically, this is just regular, not conditional SAA, will give the equal weight and use the YI observations, versus here, they using the covariate information is going to be something like this. So 1/k, if, for example, xi is a k nearest neighbor of x, 0 otherwise, that kind of thing. All right, so it basically discards some of them and uses the others. And here, what we do, we fit, for example, ordinary least squares, and then get the residuals and put it in there. So this is what we do. So we have the 1/8 ones, 1/8 weights, but we use these observations. Okay. And this is the sample size, and these are different covariate dimensions. And this is the optimality gap. So lower is better. Here we want to go lower. So for when we fit the correct model here, right, we are in advantage, of course. And so we can see that our method works pretty well, low dimension, and the same thing is true with high dimension. So we are getting significantly better values here. And this is out of 100 experiments, and these are box and whiskers plots. If we fit a misspecified model, on the other hand, so for example, if we look at low dimension here, 3 dimensions, when we have few data, our method still seems to be working well. But remember, we are fitting a linear model here. versus the k nearest neighbor, if there is enough data, will actually determine that it's a nonlinear model here, and it will do better. Our method, on the other hand, will converge to the best linear model, but it's not the right. So there's always going to be something here. But when we have small data, it seems to work actually pretty well. So in higher dimensions, of course, the curse of dimensionality of k nearest neighbor shows up. So we're still doing better with large amounts of data. By the way, the data size is proportional to the dimension here. Okay, so we can also look at as I said, our model is quite modular, right? This method, the empirical residuals method, proposed in the literature, is quite modular. So, and what we did in our experiments, if you remember, we have 3 covariates that are important, but we throw in 100, right? So if we use lasso, lasso will detect this sparsity, and especially at small sample sizes. I mean, you can see the blue ones are lasso, and they're like way better. As we increase the sample size, ordinary least squares will also start catching this. But if you know something about your model, I mean, you can do better, right? All right, same thing. Just want to mention, this is a correct model. So we have a linear dependency, and we fit a linear model. Both OLS and lasso are linear, so it's doing very well. But we, again, even when we have misspecified model, so data dependency is quadratic, but with a linear, we still see pretty good behavior, especially at small sample sizes. Lasso, again, outperforms. So at high dimensions, this is, again, we threw in 100, but it captures the 3 pretty well. Okay, so now let me check the time again. All right, so I think I'm good. Let's see. So what have we done so far, right? So we talked about, we want to solve the conditional stochastic program. And basically, we have a learning component where use your favorite method and take the empirical residuals, given their bias, etc., still plug that in and create a sample average approximation. So we looked at some asymptotic or finite sample size properties of these, and I've shown you some computational results. It's, again, a very practical method and seems to work relatively pretty well. All right, so now one criticism is this, right? We have learning, we have the sample average approximation. Already without any learning, not the conditional one, a sample average approximation, in certain cases where the problem has high variability or it has high bias, you need a higher sample size, right? But now you have the learning component, especially you're trying to figure out a conditional distribution, which is not that easy. So typically in real world situations, you have little data. And it is, what do we do in this case, right? So one thing is, it's very well known at this point that distributionally robust optimization has a regularization. Why? If I look at sample average approximation, I'm only concentrating, especially if I have few data, concentrating on those samples over minimizing. So I'm actually not doing a good decision when other random, other things can happen. My parameter can take many other values, but I haven't considered this. So distributionally robust optimization, by creating an ambiguity set, right, gives better solutions, better in the sense that their out of sample performance is superior, because it considers other things, right, that can happen. All right, so how do we do this in this setting? So basically, we use an estimated empirical distribution. So if you remember, we have a new covariate X, right? At that new covariate X, we use our estimated regression function, plug in our covariate, plus we use, from our historical data, we use the empirical residual. So each one of these n data points, right, we give them weight 1 over n. This is the Dirac measure, obviously. So this is the probability measure, distribution, etc. of the empirical residuals given this data at the new covariate x. So we use this as our nominal distribution. Okay, so this is our nominal distribution, and we create an ambiguity set around it. So we solve this empirical residuals-based distributionally robust SAA, so to speak. There's a little bit of abuse of notation here in the sense that's okay. We do min-max as usual. Here, the distribution of y, it's basically, it should be like a conditional distribution. So it's not written this way, but all of these, this is on the conditional distribution of y given x is equal to little x. Okay. How do we form this ambiguity set? Again, it's very modular. So you can do a variety of different things. So for example, if you want, you can use P Wasserstein, right? 1 to up to infinity, and we can also have infinity Wasserstein, but for that we use actually the relationship that has been uncovered in the some of papers with Barsuma, Stern, and Strutt, and some other ones using this as well. So for the infinity case, but this is also the sample robust optimization. So the Wasserstein, for example, will say, if this is the support of the y, look at all distributions that are sufficiently close to this empirical residual distribution, such that their P Wasserstein is close by some radius. And unlike the traditional analysis, this radius could depend on the covariates. Same thing here. So what does a sample robust do? This one looks at, again, discrete distributions n on n points. Let's give them the weight 1 over n. But each point can go beyond the observed empirical residual data points here. Right? So I can have, for example, here, but I can go beyond these data points, so to speak. So both of Wasserstein and sample robust, I can go beyond my current observations, or I can keep it the same support as my observations, the empirical residual. And for example, pick phi divergence, like Kullback-Leibler variation, Hillinger, your favorite, and new stuff. So again, these can go beyond the support of the observations. And this one will stay in the same. And we observe their performance is better, but solving them is also more difficult, right? Okay. I don't know if I have time for this one. Good? I think it's good. All right, let's see. So this is some theoretical results, and it's in quotations. So here, I'm letting go of some of the precision, even in the earlier one, because there were too many terms in the finite sample results. So please keep that in mind. I'm only going to give you a flavor of the results and only some of them. Okay, and to do this, let's just focus on Wasserstein P, where, as I said, we treat the infinity Wasserstein somewhat differently. So only Wasserstein P in this range. And this is just a reminder of the Wasserstein distance. And we use here the Euclidean norm to find the distance between two realizations, y1 and y2. But it could be L1 norm, etc. Okay. So just like before, right, I want to examine this. So now this is the optimal value of the ER SAA problem, but it's a robustified version. It's distributionally robust version. And this is one optimal solution. And I asked the same questions, right? So can I get, for example, will this converge to V star X and stuff like that, to the true optimal value in some probabilistic sense. I already said this, so for precise statements, please see the preprint. And again, so we have the asymptotic convergence, but I think here I only show some of them. So one thing to note is this. For example, the Esfahani and Kuhn paper, right, there are some results on the when you solve the DRO, it gives you an upper bound on the true optimal, true objective function value of the solution that you obtain from there. To do this, there's concentration inequality used and so on and so forth. So here, when we add the learning part to this, we also need some assumptions on that as well, similar assumptions, right? So before we had convergence. So now we have this assumption where we say, okay, so we look at our estimation error at the covariate x, take the Euclidean norm to the power p. So we want this to be small, or if it's going to be large, then we need it to be controlled. So we want this, if it's going to be larger than some value, we want it to be, let's say, less than 5%. Same thing for this mean errors at the training points, right? So this holds for Wasserstein of, for example, order 2, and we see the same thing, right? If this is a linear model and we have ordinary least squares or lasso, so we fit a linear model to the linear, then these coefficients have, they change order of 1 over n and logarithmically in 1 over alpha here, these reliability levels, so to say. But if we use more general regression models like random forest or classification and regression trees, something like that, we again see this curse of dimensionality. So some kind of similar story, okay? And again, here, so this is the traditional radius, for example, in Isfahani and Kuhn, and it's so that the true empirical distribution, the Wasserstein distance between this one and the true conditional distribution of y given x is equal to x should be close to each other, or if they're not, right, greater than this radius will happen with less than or equal to alpha probability. Okay, so to do this, right, again, we have the learning part. So story is about the same. Because we have the learning part, we have to inflate it. So with the same level of reliability, right, we need to have a larger radius and things like that. And that comes from the learning part that I just showed here. Okay, so we have to inflate it. And we can, under these conditions, then we can get basically the traditional results. So for example, the one that I mentioned, we have finite sample certificate guarantee, which is like, oh, if I solve the DRO, I look at its optimal value with at least some, say, 95% probability, it will give me an upper bound on the true objective function value of the optimal solution that I get from this problem. Okay. Of course, again, these are theoretical results. In practice, right? So the radius is quite large. But we can also do the same analysis with rate of convergence, right? But we need some additional conditions. For example, the risk levels have to satisfy this, right, at each sample size n. And then the radius basically must shrink to 0 so that we get the convergence of the empirical residual, the DRO version. Optimal value converges to the true optimal value with this kind of rates. Okay, and again, this rate essentially, if I go back, has the learning part, which may or may not, right, have the curse of dimensionality with respect to the dimension of x, and the traditional rate of the radius here has the curse of dimensionality with respect to y. All right. So even if we have a linear model and fit the linear here, this won't have the curse of dimensionality, but we can have on the y side of things. All right. Now I'm almost running out of time. Let's see. I'm not sure, yeah, if I can present this all, but so in practice, as I said, cross-validation is what, is an approach to specify the radius, because otherwise those are very conservative and it involve unknown constants, right? So theoretically, again, it gives us some insights, but not in practice. So we can do cross-validation. Very briefly, we can ignore the covariate information altogether, and this doesn't work that well. I have the results. This approach, you use the covariate in terms of the past covariates, the xi, but not the new information, because if you use this, this is more computationally intensive. And it turns out, at least for the problem that we looked, this in-between approach is good enough. Because we don't have enough data, approach 3 doesn't give reliable estimators. So we use the historical data, but not the new covariate information. It seems to give a pretty good rate. Okay. So we applied it to a min risk portfolio problem. I'm going to skip the details for brevity. And the setup is almost the same, right? So here we have 10 assets instead of, with the dimension of y was 30, here it's 10. And we generated them pretty much the same way, right? Here we have 3 covariates that are important, but we threw in 10 or 100. And we also took the theta. So if it's 1, it's a linear model. But even if it's 2 or 1/2, we always fit a linear model. Okay, so same setup, which is what's written here. And we solve the DRO problem, and we estimate the optimality gaps of both the non-DRO version and the DRO version. Okay, so some results here is that, so this green one that you see, same thing, dimension x 10, 100, these are the sample sizes, lower is better. And this green one is, we threw in a lot of data, so it's like the best we can do. Of course, this is not realistic. The data analyst will not have this information, but this is just for benchmarking purposes. And the 1 and 2 is basically, the blue one is the cross-validation approach 2, and it works better than them. So that's one thing. And the red one is what I presented earlier. And just one note, the sample sizes here are lower than what I've shown you before, significantly less sample size here. So what ends up happening is, right, this, if we do the cross-validation relatively well, we are getting pretty close to the ideal. This is a correct model. Same thing even when we have 100 dimensions. So like you can see the, even at small sample sizes, it's working pretty well in this case. Okay, even when we misfit the data, right, misfit the model, so to speak, we fit a linear model, but let's say it's quadratic. Again, this approach to cross-validation seems to work well and close to the ideal one. The empirical residual SAA, right, has a lot more variability. The solutions are not as good. So with this limited data, DRO absolutely helps. It works pretty well. Okay, we can also do the same thing as we did before. Remember, again, we have 3 covariates that are important, but we throw in this case, 100 of them. And ordinary least squares 1. Also, this is, sorry, this is removed the ordinary least squares. These are both on Lasso, but the blue one is the Wasserstein of the empirical residual SAA with distributionally robust, and uses Lasso with approach 2. That's the better cross-validation. And this is the empirical residual SAA without DRO, but again uses Lasso. And as we can see, the DRO one, right, especially at small sample sizes, is doing better even at higher sample sizes here. This is, by the way, the correct fit, correct model, and this is the incorrect one. So here the dimension is the same, so it's a little bit different than what I've been showing. Okay. So again, there is, with limited data, there's definitely advantage of using distributionally robust optimization. Okay, so conclusions. One more thing, and thanks to Eric here, who has encouraged us to work on this. I said at the very beginning, we assume this the errors are independent of the covariates. But we can use a relaxed assumption where we have dependency on the covariates. So this is the square root of the conditional variance covariance matrix X with respect to X, the covariates. And then there's an error here because it's multiplicative, and this is now independent of the covariates, right? but the error term here now depends on the covariates. And we can push through the theoretical results in this case, except for the finite sample, etc. is harder for sure, because there's less information about this variance, conditional variance covariance matrix. Okay, and we talked about this modular method of take your machine learning, use the residuals, and create a sample average approximation. If you have small data, create a distributionally robust version of it. It's easy to use. It seems to work pretty well. And we show theoretical results of how it works to provide some more insight, and some computational results as well. Again, right, there's a bit of trade-off in, if you know it's a nice model class of the regression, versus you can do more general, you have to pay some price. And again, because we have the learning in addition to the traditional optimization, the sample sizes, etc., or the radii, etc., have to have some blow up for this reason. Many research avenues, applications, as well as stochastic constraints, multi-stage optimization is very interesting, a discrete recourse, many things that can be done. So I will end with a thank you slide. Thank you for listening to me. I know I'm a little bit over, but not that much. So thanks very much.
Thank you very much, Guzin. It's a very nice presentation. Thanks for doing the effort to try to guide us through the two papers. It's very interesting. Are there any questions in the audience? I can either take questions through the chat, or if you raise your hand now, where do I try to see the hands? I could start while people are making their mind on their questions. So you showed us in the first part an approach that uses k nearest neighbor and your residual model. I'm wondering, I feel like one interesting thing to look at would be a mixture of the two models, perhaps, where
Yes.
the nearest neighbor could take care of the model misspecification, and yet you do have some general trends that would come from the regression models and so on.
Yeah, so that's a very interesting thing. So there are some new competitions, at least, right? So we have, Rohit has looked at, instead of using ordinary least squares, you can also use KNN within the empirical residual. So when you do this, if we fit the correct model, yes, we got a little bit, but then for the incorrect, I mean, here there's no incorrect model fit, I guess, but somehow the P also seems to make a difference, but it's hard to say. So, sorry, the theta has some difference, it looks like. What I want to say is they behave, sometimes this method is better, and sometimes this one's better when you use, for example, here, KNN. So they seem to work very similarly. So we have some new, at least computationally. But
yeah, by KNN, I mean like your residuals, the distribution you put on the residual currently is uniform, but you could also adapt that to the X value, right?
Yes, something like that. Yeah, so you fit the KNN model, and then that will give you the residuals, yeah, according to the.
Okay.
But I mean, there might be some other things. So maybe there's a different method to combine them as well. So maybe there's some future work in there to combine the reweighting plus this empirical residual, something like that, for future work. Yeah.
I was also wondering, in this experiment, how did you calibrate the size of the neighborhood for KNN? Is that something that's prescribed by Bertsimas and Kalus, or?
I don't, again, Rohit does this, I believe, so for, I don't know exactly, I don't remember at the top of my head, but I believe there's some, yeah, cross-validation and things like that. There's some already available code to determine the K and things like that, right? So what is the appropriate, how many nearest neighbors you use? So there is some work that goes into it to find the best K, and that's what we use, yeah.
Yeah, but I'm wondering if it's done at the inference stage, or is it done at the prescription stage? Like you could do the neighbors are depending on the performance on the optimality gap. You know, you choose the neighbor that minimize size of the neighborhood that minimizes the optimality gap, or do you choose a neighborhood that gives the best estimation of your demand somehow?
I believe it's the best estimation.
Okay.
Yeah.
Because your approach doesn't have any hyperparameter, if I understand well. It's really plug and play.
Yeah, no. It's very easy to just plug and play kind of thing. Yes.
So in the audience, I still don't see, unless I'm not looking at the right things. I don't see questions. You can also just unmute yourself, I guess, since there are not hundreds of people that try to talk at the same time. Fabien says it's more a comment. He's praising the quality of the talk. Great talk.
Thank you. I hope I didn't rush through it. I was very worried about time, so I kept checking my phone here all the time. Yeah, try to, as I said, I did an ambiguity set around the abstract there.
On my side, I mean, working a little bit in this area, I'm curious to know if you tried with real data, and in particular, like I feel like I struggle. The reason I use portfolio optimization is because I can access data, but in other type of operations research application, I feel the data is missing for these optimization with side information.
Yes, actually, there is a student who is he's looking at energy problem, right? So there's a lot of publicly available data, etc. So, so for example, to estimate the renewables and so on and so forth. So yes, he has looked at that, and so they are not IID, but hopefully they're like alpha mixing type of processes, so we can still push through the theoretical result. It still seems to work. So in that setting, at least with real world data, yes, it could work. So that's at least one application that I'm involved in, and yeah, seems to work.
And what's the side information there?
So the side information, so for example, in the renewable, right? So you can use the weather patterns, the past, the seasonality, time, day information, and things like that. And then temperature, precipitation, that kind of stuff, wind, and some climate variables. Yeah. So the climate one obviously is not IID. But it seems to fit in relatively good statistical behavior there, so that we can push this through. Yeah.
Because there's a real challenge when you're using real data of engineering the features. It's either you have only a few variables that you're keeping track of, and it's not really interesting, or you have so many, like your temperature conditions could be over a very large area, and then you have a map of temperature or wind speeds, and how do you convert that into a regression model without overfitting and so on? It's very challenging.
Yeah, just that part is challenging. Yeah. And then you have to do that well to put into the optimization. Yeah, correct.
Okay. Well, we can pursue this conversation.
Yeah, it seems like it.